everybody. So today we're going to go through slides 20 through 34, which have to do with your acid-base reactions, and then also neutralization reactions. Then we're going to go through slides 35 through 39, which have to deal with gas formation reactions. We've done some stuff with acids and bases before. The gas formation reactions will be new, but still I want to go through acids and bases kind of like we haven't really done that before. And then we'll do gas formation reactions as well. If we get time in class, then we'll go ahead and start that gas formation video. If not, then I'll want you to finish whatever you didn't get to watch in class for homework tonight. And then tomorrow we're going to do slides 39 through 49, which have to do with oxidation reduction reactions and then single replacement reactions. And then on Wednesday, I'm going to have you practice all of those different types of reactions that we've learned. Because the most important part for this chapter is that we really understand how to write all of these different types of reactions. And the only way that we're going to get really good at it is if we practice it over and over and over again. And then on Thursday, we're going to continue to finish off your slides for chapter 4. I'm not really positive what the end is. Molarity and titration. So we'll do that at the end. That's the end of chapter 4. And then Friday, you're going to have a homework day in class. So you'll bring your homework in like you've done the last 3 chapters, ask questions that you have. And then this coming weekend, I would like to offer, if you want to come to that Deerfield Town Center Starbucks, I will be there at noon on Saturday. So if you want to study for your test, if you have other questions, come to that Starbucks on Saturday at noon. That's the only time that I'll be there at Starbucks is at noon. And I'll stay until however long we need to, until everybody feels comfortable with their questions. But yeah, if you want to come in and ask questions, you want to study, then I'll be there. So then hopefully that kind of helps for your Chapter 4 test, which will be on Monday. And your Chapter 4 test, on Monday, you'll need to bring your Chapter 4 homework questions because those will be due on Monday as well. And then that next week, on Tuesday, we're going to start thermochemistry, which is Chapter 5, and it'll be super fun. And then the following week, I'll be back. Yay! Okay, so let's go ahead and get started on acids and bases. This is slide number 20 for Chapter 4. So in terms of acids, we first started thinking about acids because of a guy named Svante Arrhenius. He was a Swedish physicist and chemist, and he had originally defined an acid as something that is going to increase the hydrogen ion concentration when it's dissolved in water. Now remember that Arrhenius also said that a hydrogen ion, I can also just call that a proton. But why can I just call the hydrogen ion a proton? So why is H plus equivalent to just calling it a proton? Well, now I know that hydrogen has the atomic number 1, meaning that it has 1 proton. So I know hydrogen has 1 proton. And I also know that the atomic mass of hydrogen is 1. So then that means that how many neutrons? Well, if my number of neutrons is mass minus number of protons, the mass is 1, I have 1 proton for hydrogen, so that means hydrogen is going to have 0 neutrons. But last I need to find out how many electrons does this hydrogen ion have? Well, if it wasn't the hydrogen ion, let's say it was just a neutral hydrogen. I just had a hydrogen atom all by itself. Then I would say that it would have 1 electron because the number of protons and electrons is going to be equal in a neutral atom. But this has a positive charge. That means that it's going to have 1 more proton than it does electrons. Well, it has 1 proton, so in this case, it's going to have 0 electrons. So if I look here, I have 1 proton, 0 neutrons, 0 electrons. So this is telling me that a hydrogen ion is the same thing as saying that I have 1 proton. So that's why we can use those 2 terms interchangeably. I can say hydrogen ion, or I could just say proton. And Arrhenius is the one that really helped us with that. Okay, so Arrhenius says that an acid is defined as something that can increase hydrogen ions, or the concentration of hydrogen ion when it's dissolved in water. So I have an aqueous solution. If it's an acid, that hydrogen ion concentration, or the amount of hydrogen ion that I have, is going to go up if it's an acid. Now, Arrhenius, his definition of acid was good, but then Bronsted and Lowry came along, and they defined it in a little bit of a different way. They said that an acid would be something called a proton donor. So if it was an acid, if a substance is really an acid, it wants to give away, or it will give away, that hydrogen ion when it's in a solution. And we're going to talk more about that in a few more slides. Now, lastly, we have another theory about acids, and that's the Lewis theory. Now, Lewis defined acids as electron acceptors, and according to AP, right now, the only two theories of acids and bases that they're focusing on are Arrhenius and Bronsted-Lowry, with, I think, more of an emphasis on the Bronsted-Lowry one. Lewis isn't so much as accepted as of right now, but again, I mean, that may change. So as long as you know that Lewis defined acids as electron acceptors, then we're good to go. The ones I think that are really more important for your AP test are Arrhenius and then Bronsted-Lowry. So Arrhenius says that acids will increase the concentration of hydrogen ion, and then Bronsted-Lowry just says that acids are considered to be proton donors, which will also show an increase of hydrogen ion in solution. We also know that there are 7 strong acids, and if it's not an acid on this list, it is not a strong acid. So we have those 7, I have listed them here. You do need to have these memorized. So we have hydrochloric, hydrobromic, hydroiodic, and then we have nitric, sulfuric, chloric, and perchloric. Let's look and let's see, the only polyprotic acid that we have is H2SO4. And remember, polyprotic just means that we have more than one hydrogen. So this acid would have one hydrogen, one hydrogen, one hydrogen. Remember, we call this monoprotic, meaning one. Monoprotic, monoprotic, monoprotic. So sulfuric, only one that has, or that I would call a polyprotic acid, meaning it has 2 hydrogens. Okay, so, and here we go again. About polyprotic and monoprotic. So molecules of different acids will ionize to form different numbers of hydrogen ions. So monoprotic acids are only going to yield 1 hydrogen ion. So once that acid can dissociate in water, I'm only going to get 1 hydrogen from that acid if it's monoprotic. If it's diprotic, then I'm going to get 2 hydrogen ions for that one acid. And diprotic would be under that category polyprotic, so poly meaning many hydrogens. For a polyprotic acid, remember that the acids, or the hydrogens, are only going to ionize 1 at a time. So I'm only going to get 1 hydrogen ion at a time. So let's say we take our only polyprotic strong acid, which is H2SO4, and it's going to ionize once it is dissolving in water. And as it's doing that, it's going to lose 1 hydrogen first. So I'm going to go from H2SO4 to my hydrogen ion and then HSO4 minus. Well, now this can lose a hydrogen ion when it's in solution. So now what I'm left with is going to ionize, and it's going to give off that hydrogen ion. So let's say here, that's the Bronsted-Lowry definition, that I'm donating that hydrogen ion. So here's my acid being a proton donor. It's giving away that hydrogen ion. So I have my HSO4 minus here. It's donating an H+, and then I'll be left with that sulfate ion. And we know that acids have to have something called an ionizable hydrogen. Okay, so an ionizable hydrogen, we have said ionizable hydrogen just means that's my hydrogens that will be able to dissociate when they go into water, or when they're in that aqueous solution. So I want to see how many hydrogen ions could be generated by each citric acid molecule dissolved in water. So I need to look here. Here's my molecule of citric acid, and I want to know how many ionizable hydrogens. Well, an ionizable hydrogen is something that is usually attached to a very electronegative element. So if that hydrogen is attached to an electronegative element, then it's easily ionizable, meaning that it will easily come off in that solution. So if it's very electronegative, I see that this hydrogen is attached to carbon. Is carbon a very electronegative element? It is not. Well, this hydrogen is attached to that carbon. So is that one, so is that one. But this hydrogen is attached to oxygen. So is this one, so is this one, and so is this one. So I have 4 hydrogens that aren't attached to a very electronegative element, carbon. I don't have a big electronegativity difference here. But oxygen would be like the second most electronegative element on the periodic table, and hydrogen is attached to it here. So if I had to guess how many ionizable hydrogens citric acid would generate in water, I would say 4, because I have this hydrogen that's bonded to a very electronegative atom, oxygen here. I have this hydrogen bonded to, again, an electronegative element, oxygen here. Same thing here, same thing here. So an ionizable hydrogen is a hydrogen that will be generated, or a hydrogen that will dissociate in water in an aqueous solution, as long as I see that it's attached to an electronegative element. So oxygen is a good one. We know fluorine is the most electronegative element. If we think about our electronegativity differences, then that's how I'm going to be able to determine if it's an ionizable hydrogen. So mostly we will see if hydrogen is attached to oxygen, you're good to go, because that's what it will be in most of these cases. Okay, so we talked about acids. Let's talk about bases. Now, again, we said that we had those 3 theories of acids and bases. There's Arrhenius, there's Bronsted-Lowry, and then there's Lewis. So in the Arrhenius theory, he defined a base as a substance that increases the concentration of OH- or hydroxide. Now, there was a problem with Arrhenius' theory because of his definition of what a base was. Now, do all bases have hydroxide, or do all bases need hydroxide to be considered a base? They do not, because Bronsted and Lowry found that later on, when they were working with ammonia, ammonia acts as a base. Remember, ammonia is NH3, and it will act more like a base. So, Arrhenius' definition of a base, that a base is something that increases concentration of hydroxide when it's in water, that's true, but it doesn't account for all bases that we know of. So because of that, it's limited. It's still true if we have bases that have hydroxide in them, but it doesn't cover all of our areas. So Bronsted and Lowry kind of generalized, I think, more of Arrhenius' definition by saying that a base then must be a proton acceptor. So Bronsted and Lowry said that an acid was a proton donor. So if the acid is going to donate the proton, well, where's that proton going to go? Proton's going to be accepted then by the base. So Bronsted and Lowry say bases are proton acceptors, acids are proton donors. And then our last acid-base theory is a Lewis. Lewis said that acids are electron acceptors. Well, Lewis will just define bases as electron donors. We also know properties of acids and bases. So if we use litmus paper, if the paper is blue, the litmus paper turns blue, it's a base. If the litmus paper is red, we know that that means that it is an acid. Now, other properties, acids we know, bases we know can feel slippery. We also know that they, for the most part, can end in hydroxide, but that's, again, Arrhenius' limited definition. They turn litmus paper blue. Acids, we can say that they're sour, even though we shouldn't be going around tasting acids. But if you had, like, orange juice or, like, lemon juice, stuff like that, they have some types of sour tastes to them. We also know that bases then would have bitter tastes. Again, we shouldn't be going around tasting bases, so I'm not telling you to taste acids and bases, so please don't do that. And let's keep going. Okay, strong bases. So we know that there are 7 strong acids, and then we said that there were 8 strong bases. So the strong bases are the soluble metal salts of hydroxide ions. So any alkaline metal with hydroxide. So we have lithium hydroxide, we have potassium hydroxide, sodium hydroxide, we have rubidium hydroxide, and cesium hydroxide. So all of those alkaline metals with hydroxide would be a strong base. And then any strong base or any hydroxide ion with calcium, strontium, or barium is also considered to be a strong base. So there are 8 of them here that we'll need to memorize. Okay, so in an acid-base reaction, we know that the acid is what's donating the proton, or that's at least just according to Bronsted and Lowry. That's what we know so far. So acid is a proton donor, meaning that it is going to give up that hydrogen ion, and it's going to specifically give up that hydrogen ion to the base. So in this case, I have water reacting with ammonia, NH3. So if I look at my products over here, I produced ammonium ion, so I produced NH4+, and then I also produced hydroxide ion, OH-. So if I look here at my reactants, I had NH3, but then on the product side, I see that NH3 gained a hydrogen ion to become NH4+. So in this case, I see that my NH3 is going to accept that hydrogen ion. So if that is accepting the hydrogen, NH3 must be my base. H2O, water, on my reactant side, if I look over here, my product side, OH-, I see that this water then gave up a hydrogen ion, meaning then that it must have donated the hydrogen. So since it's a proton donor, or that hydrogen ion donor, it must be my acid. So I have the acid and the base. My acid is giving that hydrogen ion, or it's donating that proton to NH3 to produce my ammonium ion and my hydroxide ion. Okay, so we labeled acid-base. We said this was the acid and this was the base. But we also have something called a conjugate acid-base pair, or conjugate acid, conjugate base. Now, we have said that a conjugate acid is something that will accept the hydrogen ion. So the conjugate acid is something that will accept the hydrogen ion, and the conjugate base is something that will remove or release the hydrogen ion. Sorry, guys. Okay, so conjugate acid, let's repeat that again. Conjugate acid is something that accepts that hydrogen ion. So here's my acid, here's my base. Well, what over here on my product side, what accepted that hydrogen ion? Was it the ammonium ion, or was it the hydroxide ion? Okay, well, my ammonium ion accepted that hydrogen, or that proton. So because this accepted the hydrogen, I'm going to call that my conjugate acid. So I had my base, it accepted that hydrogen, and it became then the conjugate acid. Now, conjugate base then is something that's created from removing that hydrogen ion. Well, water donated the hydrogen ion to ammonia, so because it donated, I created this hydroxide ion, so this must then be my conjugate base. So conjugate acid is something that will accept, it's what I've produced. Conjugate acid is in the products, and that's the one that accepted the hydrogen ion, and then my conjugate base is in the products, and that's what I see where I removed that hydrogen ion. Okay, so let's make sure that we're able to label then, if we were given some type of reaction like this, make sure that you're going to be able to label acid-base, conjugate acid, and conjugate base. If you want more examples with these, I think there are a few in your homework, but if you want more examples of these, email me, post on the blog, let me know, and I'll put up some more examples for you just so that way we can have more practice. Okay, so reactivity of strong and weak acids and bases. Most of the time we consider reactivity to just be, if we're thinking about acids, to just be dependent on the hydrogen ion concentration. It is so easy for us in terms of acids to think about reactivity in terms of hydrogen ion. If I have a lot of hydrogen ions, then I consider the reactivity of that acid to be strong. Strong acids are more reactive than weak acids then, because a strong acid will always completely dissociate. So that means I'm always going to get hydrogen ion whenever I dissolve a strong acid in water. But a weak acid, I'm not going to get as many hydrogen ions because they can only partially dissociate. They won't dissociate all the way, so that means that a weak acid will never have as many hydrogen ions as a strong acid would. Now, the reactivity of an acid, though, could also depend on the anion concentration. So, for example, hydrofluoric acid is a weak acid because it's not part of my strong acid list. But it's a pretty strong weak acid, and it's very reactive, and it will attack many substances. Now, fluorine, we know, is very electronegative. And because fluorine is very electronegative, for the most part, hydrofluoric acid it does partially dissociate, but it dissociates more than a lot of other weak acids. So because of that, it's considered to be on the stronger side of the weak acids. So for the most part, we consider reactivity in terms of how many ions an acid can produce, or how many ions can a base produce. But sometimes it can depend also on the anion concentration. But we usually only think about it in terms of strong acids. Okay, so let's look at an example here. I have 3 different compounds here. I have 3 different samples. I have HX, HY, and HZ, and they're all acids. And I want us to rank these 3 solutions in terms of, or from the strongest acid to the weakest acid. So let's look at their strength, acid strength. Which one would be the strongest acid, and then which one would be the weakest acid? And I want you to write down for me why. Why do you think that is? So right now, tell me which one is the strongest acid, which one is the weakest acid. And if you wouldn't mind pausing the video for a second, so then that way you can do this, and then I want you to talk about it in class. I want you to come up unanimously as a class with your answer. So someone pause the video for me. Okay, so if you said that the strongest acid was HY, you would be correct. HY is your strongest acid. Why would HY be the strongest acid? Because it's completely dissociated into its ions. Reactivity or strength of an acid is all about how many ions are present in that solution. So HY has the most ions of the 3 that I gave you. So because HY is completely dissociated, it has to be the strongest acid. Because we know that strong acids completely dissociate. Weak acids only partially dissociate. So strong acid, I have a full dissociation here. So HY is the strongest. But then what would come next? What would come next? So HY was my strongest. If you said HZ, you would be correct. So HY is the strongest, HZ would come next, Hz comes next because I have three cations, three anions here in terms of ions, but then in Hx, I only have two cations, two anions here. So Hz has a few more ions present, so because it ionized more, I consider Hz to be stronger than Hx. So Hx in this specific case is going to be my weakest acid, and that's because it didn't ionize as much as Hy or as Hz did. Okay, so we talked about strong and weak electrolytes at the beginning of this chapter, but we're going to talk about them just a little bit more because acids and bases are all about strong and weak electrolytes. So we saw this table again earlier. So let's classify these compounds that I gave you here as either a strong electrolyte, a weak electrolyte, or a non-electrolyte. Now remember, a strong electrolyte is something that we can see here in our table is considered to be an ionic compound, it's a strong acid, or it's a strong base. If it is a weak electrolyte, we consider it to be a weak acid or a weak base, and a non-electrolyte would just be considered any other molecular compound. So it's a strong electrolyte if it's an ionic compound, a strong acid or a strong base. It is a weak electrolyte if it's a weak acid or a weak base, and if it's anything else, it is just considered to be a non-electrolyte. Okay, so classify the following again: strong, weak, or non. CaCl2, so I have calcium chloride. Well, calcium chloride is an ionic compound because that would be a metal and a non-metal, and because that's a metal and a non-metal, it is ionic, and ionic compounds are all strong electrolytes. So CaCl2 would be a strong electrolyte. HNO3, that is one of those 7 strong acids that I had to memorize. If it is a strong acid, we know it dissociates completely, and we know that ionic compounds, strong acids, and strong bases are also considered strong electrolytes, so HNO3 must be a strong electrolyte. C2H5OH, this is ethanol. C2H5OH, ethanol. Well, it's not an ionic compound. It's not a strong acid. It's not a strong base. I don't see that to be an acid at all. Doesn't look like a base at all. So this just must be considered like any other compound. So C2H5OH, ethanol, I would call that a non-electrolyte. Let's go to the next one. I have formic acid, which is HCOOH, formic acid. Okay, it's an acid, so I just need to determine if this is a strong or a weak acid. Well, is formic acid part of my 7 strong acid list? It is not. So since it's not one of my strong acids, it must be a weak acid. So as soon as I know it's a weak acid, it must be a weak electrolyte. Lastly, I have KOH, potassium hydroxide. I have KOH. That is, I know, a part of my strong base group that I had to memorize. So it's a strong base, or I could also just say that this is an ionic compound. And so since it's an ionic compound, it's a strong base, it must be considered a strong electrolyte. Okay, next one. I want us to rank the following compounds that are dissolved in water, and let's assume they're all of equal concentration. Rank the following compounds at equal concentration that are dissolved in water in order of increasing electrical conductivity. Let's think about this. I need to get to what's going to give me the most electrical conductivity. That means if I put in a light bulb, or if I attached electrodes to a light bulb in each of these solutions, which one would shine the brightest? So, and then which one wouldn't shine at all, or shine, or be very dim? So we also said reactivity or electrolytes have to do with ions. Okay, how could I rank these? Increasing electrical conductivity. So I need to find which one would be a non-electrolyte or weak electrolyte first. Of these 4, I have calcium nitrate, I have glucose, I have sodium acetate, and then I have acetic acid. Are any of those non-electrolytes? Well, calcium nitrate is an ionic compound. All ionic compounds are strong electrolytes, so this is strong. C6H12O6, glucose. It's not an ionic compound, it's not a strong acid, it's not a weak acid, it's not a weak base. This is just a normal, considered to be one of those other molecular compounds, so that is a non-electrolyte. Sodium acetate, metal polyatomic ion, ionic compound. So if it's an ionic compound, it must be strong electrolyte. Lastly, acetic acid. Acetic acid isn't one of my 7 strong acids, so then that means that since it's not one of my 7 strong acids, it must be a weak acid. So we said strong electrolyte, non-electrolyte, strong electrolyte, weak electrolyte. So I need to rank these in order of increasing electrical conductivity. So non-electrolytes have no electrical conductivity, so that means glucose must go first, because we said it was a non-electrolyte. What would come next? Well, the next one would be my weak electrolyte. That means that I'll have a partial dissociation of ions, so I may get like a dim light coming, I may get a little bit of electrical conductivity, but I'm not going to get anything like what I would with a strong electrolyte. So this was my non, so this would be first, glucose. Acetic acid was my weak electrolyte, so that would come next. But now I have these 2 strong electrolytes. So which one comes next? Remember that electrical conductivity, or electrolytes, have all to do with how many ions are present in that solution. So if I broke this apart into ions, sodium and acetate, I would get 1 sodium ion and I would get 1 acetate ion. If I broke calcium nitrate up into ions, I would get 1 calcium ion, but I would get 2 nitrate ions. So this gives me a total of 3 ions. This compound only gives me a total of 2 ions. So if this has more ions, this is going to hold that electrical charge, or it will allow more electrical flow in the solution. It will carry more current in the solution. So this is my non-electrolyte. I would say this is first. This was my weak electrolyte. This would come next. Because this doesn't produce as many ions as calcium nitrate, this would come third. And then my best electrical conductor would be calcium nitrate, because it would give me 3 ions compared to sodium acetate, which would only give me 2 ions. So again, if we want more practice with this, email me, let me know, and we'll post some more on the blog just to get you thinking about some more questions like that. Okay, in terms of neutralization reactions, so generally we know when solutions of an acid and then a metal hydroxide base are combined, we get our products to be salt and water. So I have an acid reacting with a base. When I have an acid-base reaction, I form salt and water. Salt and water. That's an acid-base reaction, aka neutralization reaction. When a strong acid reacts with a strong base, we specifically form every single time water. That is the biggest thing for a neutralization reaction. So when a strong acid, and it's only when we're reacting a strong acid with a strong base. So in this case, I have hydrochloric acid, which I know is one of my 7, sodium hydroxide, which I know is one of my 8 bases. When those 2 react, I'm going to make salt, really in this case salt, table salt, and water. But if I look then, this was my molecular equation. If I write the complete ionic equation, I have hydrogen ion, chloride ion, sodium ion, hydroxide ion, sodium ion, chloride ion, and then water. Chloride ions cancel, sodium ions cancel, so I'm left with hydrogen reacts with hydroxide to form water. So really, when a strong acid is reacting with a strong base, what is really happening in this reaction is I'm producing water.